Alright, the third problem we're going to do now is we're going to switch gears a little bit and use the new cylindrical shells method instead of the disc slash washer method. Main reason we do this is because with the disc method, if we want to rotate about this line some shapes that look like this, we could easily do that because we can make a perpendicular slice, thin slice in the horizontal direction. And now we would look at this and say, oh, that's easy. The outer radius is here, inner radius is here, and then just subtract them. Well, the problem now with this is, let's say we have a new graph, something that looks like 4y squared minus y cubed. So we don't know exactly what this looks like right away, but we can also rewrite this as, if we pull a y squared out, we can write this as y squared times 4 minus y, which gives us zeros of 0 and 4 on the y-axis. So now we know it crosses 0 when y is 4 or when y is 0. And now when y is between 0 and 4, we've got a positive times a positive. So it's going to go positive here, and it's going to end up looking something like this. Alright, the problem with this now, though, is that we cannot... So this is also bounded by the line x equals 0, which is just the y-axis. And we want to rotate this area about the x-axis, right here. Well, the problem now is if we make a perpendicular slice, like we've been doing, we now make a perpendicular slice. Our outer radius and our inner radius lie on the same curve, so there's no real easy way to define outer minus inner when they're both represented by the same equation, 4y squared minus y cubed. So now what we have to do instead, trace this again. Remember, it's at 4 and 0, looks something like that. And now what we do is we will have to make, so this is our axis of rotation, it's horizontal, so we're actually going to make a horizontal slice as well. Alright, so now if we blow up this part of it over here, this should look something like, we've got something like this, crosses there at 4. Now we've got these slices that we're going to rotate about the x-axis. So what's going to end up happening is we're going to have something that looks like, now if you imagine in your mind this rotated 90 degrees, that looks something like a can or a cylinder. So now what we have, we know that the area of a cylinder is pi r squared times height. But this cylinder also has some tiny thickness, so there's a, we'll call it a width for now. And actually it's not pi r squared because that's the area of the circle. We want 2 pi r times h. Yes, so we want the circumference of the bottom here. The circumference of a circle is 2 pi r times some height, and then also some small thickness and width. Alright, so now our radius of our cylinder is just going to be from our axis of rotation up to the point that we have this thin slice, and this is a vertical displacement, and generally we call that y. So our radius will just be the distance y. Now our height is the distance running from the axis up to the curve, which in this case is rather convenient because that's just a horizontal displacement, and we would generally call this x. So now we have our height is x, and now our width is just this really thin slice that we've had down here. And we know our really thin slice gives us a tiny displacement in the vertical direction. So this is actually going to be dy. So our width is dy. And now we are ready to set up our integral. So now we have 2 pi out front. Radius is just y. Height is x, and width is dy. And now with dy comes a couple different issues. One, we cannot have this x in here. We need to replace that. And also, since we have dy, we have to integrate from the 2 different y values. Well, earlier we found the y values where it was 0 were at y equals 0 and y equals 4. So that gives us our values there. And now our x, well, our x is following along the curve that we defined as x equals 4y squared minus y cubed. So now we can just substitute x for this entire expression. So our new integral will become 0 to 4 with 2 pi outside of y times x, which is 4y squared minus y cubed. Then we have still dy out there. So now we're basically ready to integrate it. It would be easier to simplify this by factoring through that y. So we're going to write that as, instead I'll just erase this. So factoring that y in there would make this a cubed. It would make the y cubed a y to the 4th. So really what we have is 4y cubed minus y to the 4th. That is a 4. And we still have dy out here because we have not integrated yet. Alright, so now we are ready to actually integrate. So once again, when it comes down to the integration for these things, it's not that difficult usually, because it's power rule that we've already learned and practiced a whole bunch. So this becomes 2 pi times increase the power by 1 to 4 and divide by 4, so making those 4's cancel. So we just have y to the 4th minus y to the 5th over 5. And this is evaluated from 4 to 0. But once again, just like in the last problem, if we plug 0 in here, we get 0 minus 0. We don't have to worry about plugging in 0, we only have to worry about that 4. So we end up with 2 pi times 4 to the 4th, which is going to be 256. And then if you subtract y to the 5th over 5, that is actually going to become 256 times 4, which is 1024 over 5. Alrighty. So now, here we are technically done. In general, you'll want to simplify. So I'm going to erase this last part just so we have room on the bottom. So now we can simplify what's in the parentheses here and write that as 1280 over 5 minus 1024 over 5. This is all multiplied by 2 pi. So now if we have 1280 minus 1024, that gives us a sum of 256. Imagine that. And this is going to equal 256 over 5 times 2 pi. Or if we want to distribute it through, we get 512 pi over 5. That will be our final answer for this first cylindrical shells problem.